Yeah.
Okay, and as usual in this meeting, everything works well again. And I'm glad to announce Tuomo Valkonen from University of Liverpool with a question which might bother a lot of us. What do regularisers do?
Indeed, although to some extent, and to really continue with the movie theme of the previous talk, this talk is kind of from a time long ago and a galaxy far away, because my regularisers are constructed by hand and have only a few parameters. There is no deep learning here, although there will be some bilevel learning later to study the regularisers. But really, we don't know much about these old-fashioned constructed regularisers either, really. What do they do? And we know even less about deep learned regularisers. We mainly know that the deep learned regularisers seem to work until they completely break apart. Like we saw in Anders Hansen's talk earlier today, you can fool deep learning very easily. There's even some studies that show that you can only have to put a few pixels somewhere and they will be completely lost often. So we really need to understand these things better. And I will start with some simple constructed regularisers that were popular a few years ago, not so much anymore. And the first thing we could of course ask when we want to solve any problem is, what is a good regulariser for this problem? What is the best regulariser for this problem? Yeah, and without even seeing any data, because that's a lot of work to deal with data. So if you could just have an analytical criteria that would tell us, okay, for this kind of data that we expect to have, this kind of regulariser will be good. Or just tell if there's any good regulariser known for this problem. And also, we should know that our regularisers work, that they don't introduce artifacts. Like if we want to detect, let's say, cancer in an image, and if we do obtain the image through some processing inversion of some data, that what we see in the image is not a product of the regulariser, that it's actually in there in the real world. And otherwise as well, what kind of other distortions they might introduce. So these are the kind of questions I will be looking into a little bit in this talk, mainly analytically. And I will start with the artifact question. And really primarily and mathematically, the question whether regularisers introduce edges into images. So edges would be where if you have an image, and let's say some blob there, and you approach this part line here from this side and approach it from this side, then the values will be different. That would be technically an edge. And since actually I will be working in the space of functions of bounded variation, there would be a more measure-theoretic definition of that. But here is basically the question. Or mathematically, I will be mainly looking at denoising problems, because already they are actually difficult to analyze. And anything more interesting is even more difficult. It has not been done. So I want to denoise, I have some regulariser, and the last line here just says mathematically that in the solution image U, there will be no edges that are not in the original image, basically, in terms of Hausdorff measure and so on. And I want to answer this question for specifically total generalized variation. This whole research, which is more general, was started by wanting to answer this question for the second order total generalized variation, which is here. It's just dV, and then you subtract some W out of the gradient and penalize that as well, and that way you balance between first and second order features and actually get better results. And it has 2 parameters only, not million parameters or something. But let's start with regularisers from a time even long before TGV. It's just basic total variation. the basic total version is very nice because it has a so-called co-area formula. So you can actually represent the total variation as an integral over the perimeter lengths of all level sets. And you can analyze many things about total variation through the level sets, through the perimeters. And actually, just total variation denoising problems turn out to be minimal surface problems on the level sets. So there is a proof from 2008 that total variation doesn't introduce edges. It starts like this. We supposedly have an edge here in our solution image U, which is sketched here. We extract a level set, which is here, like this, and supposedly it jumps here, and in particular it jumps at some point here, and now we extract another level set S. And actually, it turns out that S is lower level set. It turns out that if there would be a jump, so there would be a point where basically the level sets agree, then the lower level set would have to be inside the upper level set at some point, and that's a contradiction. That you obtain that through some regularity properties of PDs and minimal surfaces. It's quite nice proof. But how to do this for TGV? It doesn't have a co-area formula. Well, in one dimension it's quite easy. Here we again have our original data F, a supposed solution U, which jumps at this point. Well, we can in this case just add a simple step function to it, which basically shifts the jump from this part to this part, so it doesn't actually change the TGV or total variation term by doing that, and it improves the fidelity term, and that way you reach a contradiction. There cannot be any new jumps introduced. This is easy in one dimension, but things get quite tricky in higher dimensions. And we need to do also some two-sided things in one dimension, but that's not so important here. So again, I'm trying to sketch something here. We have a supposed solution U and the original data F, and we try to do the same thing here. There's supposedly a jump here. This is the same thing seen from above. So instead of adding a simple step function, we add basically a step function out of a simplex, or a simplex modified a little bit to match the edge here in the image. One might think that it should work the same, but things get trickier in higher dimensions. If you look from above and look at this, like this part of the jump would be removed, but this simplex adds actually a longer jump here. So it doesn't work in a simple way. You might think that things can work out if you kind of blow up and add smaller and smaller simplex there, but the problem with functions of bounded variation is that they are like very measure theoretic objects in a way. The jumps can actually be kind of point clouds. There doesn't necessarily exist a part. If you have an edge here, it's not necessarily of some height higher than epsilon at any small stretch here. It may be very small in parts here, and you cannot like blow up the edge at point and get a part of the edge where the jump is high. So that's why this kind of argument doesn't work. But there is some modification which took a couple of years to find that does work. Now again, supposedly have a edge modeled by gamma here. I take some domain U around it, then I construct kind of transformation of the domain that just moves it a little bit around. Let's say moves this line here to the gamma and moves gamma to this other line here. So this is a transformation of Lipschitz transformation of the domain. And then what I do is I push forward the supposed solution U by this gamma, and I also need to do some convex combinations to just make a small change. And now I think this might work. It doesn't quite work. There are still some difficulties. Now here we again have the same jump here, gamma, but it has a very high curvature. So if I shift this jump forward, it will add a lot of edge there because the curvature is high. So actually, in this case, we have to do the shift backwards. And it turns out that kind of averaging these two possibilities, this transformation will work in some cases. I get something I call the double Lipschitz comparison condition. So I have my regularizer R, which satisfies this double Lipschitz comparison condition if, and I take two Lipschitz transformation of a domain where it supposedly jumps or doesn't even need to jump, and kind of average over those two Lipschitz transformation, subtract twice the original, and then there is some specific constant that bounds this difference. And now, if I construct some very specific Lipschitz transformations, this constant here will be quite small, much smaller than the improvement the same transformation causes on the fidelity term. And that way I can get a contradiction and show that there can be no edges introduced by the regularizer, the denoising problem. Now, this unfortunately still doesn't work for TGV. It works for total variation, for which we already had a proof. It also works for Huberized total variation, so smooth total variation, which is often used in practice. It would also work for kind of Perron-Malik anisotropic diffusion. It would work for kind of non-convex total variation models if these models were well posed, but they don't actually have solutions in PV. They are very ill-posed approaches. It still does not work for higher order models like TGV or informal convolution TV, which came a few years before TGV. We need to do a small kind of partial push for a trick that I won't really go into here, and after that we can almost make the approach work on many higher order regularisers. For TGV, it still doesn't work. We still need to know more about the structure of the space of functions of bounded deformation, which is a pretty nasty space. And generally, for other regularisers, which you will see in the next slide, we will need to be able to answer the local boundedness of the solutions. This is also not known for these higher order regularisers, whether the solutions to problems involving them are even locally bounded. But for the special case of informal convolution total variation, in 2 dimensions, there's a result of Demengel, which says exactly that the whole so-called PV2 space is embedded in infinity, so we can get the boundedness easily from that, and that way we have a result that in 2 dimensions, so for typical images, informal convolution total variation cannot introduce edges. Then we can also get some partial results for variance of total generalized variation if we assume that the solution is bounded locally. So we can change the total generalized variation to not symmetrize the gradient in the second order term, or we can change the second order term to not use the one norm but use some other norm. Then this works, because in these cases so-called Korn's inequality holds. The tricky part with the space of functions of bounded deformation is that so-called Korn's inequality doesn't hold. So that's the missing part. Here is something just showing if we change into the Q norm here in the second order term, we basically get practically the same results. So there exists a regularizer that practically works the same as TGV, and that probably does not introduce new edges into the image. So it does not introduce new artifacts of certain kind, which, well, many objects are separated in images by edges from other objects. So that's one thing, trying to study whether artifacts are introduced. The other thing is, can we really even improve images by processing them and really know it a priori? So here again, just to recall, 2 second order regularisers TGV and ICT. We both have 2 parameters which we have to choose somehow. And how to choose them? Well, this research actually into whether the regularizer works started from bilevel learning, trying to optimize these parameters. They're trying to prove that this works. And why we might want to optimize? Well, here are some experiments with different values of alpha and beta for TGV. Here is kind of a good optimal solution. If we make the second parameter very low, then we get lots of oscillations. If we made it high, then we get like a TV-like result which is staircasing, which we also do not want. And if we choose alpha also wrong, then we can get blurriness and so on. That we need to be able to choose them in a good way, and because there's more than one parameter, it's already more difficult than TV, but still much easier than choosing the parameters for some deep learned regularizer. And many people have studied these bilevel optimization based approaches for learning. First, just parameters for simple models, but these days people are already also learning forward operators using this bilevel approach, not just deep learning. So here we have some cost functional which measures against some ground truth or other criteria whether the solution U alpha we get from our image processing model, which is the inner one. So it measures how good this solution is and tries to find the best parameter. And in this talk, our specific image processing objective is like this. So there is a fidelity term, there is some k, and there is a kind of sum of norms of some operators of U. It looks a little bit like this higher order regularizers, but it's more general. You have to choose your A's and K's intelligently to get kind of as a marginalization, either TGV or ICTV out of it. Like this, and TV as well comes out of this easily. But that's not really important. You can construct this kind of bilevel frameworks. But we are mainly now interested in using it for just a couple of simple cases. We have some noisy data F, we have ground truth, we focus on the denoising in the inner problem, so just try to find the best parameter for TGV denoising. And then we choose a couple of different costs at the outside. The first is just the usual like L2 cost or PSNR. Another is basically using TV as the cost, but we apply smoothing to it to be able to compute things. And then there's the problem that the solution mapping of the inner problem is actually set valued, because the inner problem is not smooth at all. So for numerical purposes, we have to smooth it at the current state of algorithms. So we add some Hooper regularizing to these norms here, and we also add some Hilbert space smoothing term at the end. Now, what we would like to know is whether these solutions also converge to the original solution with epsilon and gamma, epsilon equal to 0 and gamma equal to infinity, and whether this original problem here even has a solution. So with the Hooper regularization in the Hilbert space regularization, it's quite easy to show that the learning problem has a solution. But in the original case, this is really more interesting from an analytical point of view, where we don't apply any additional numerical regularization. It's not so easy to show that there even exists an optimal parameter alpha. Because actually we cannot let alpha go to 0. That causes some problems in getting convergence in the space of functions of bounded variation. But at the same time, we wouldn't want to add any constraints on alpha, because we could easily just add a lower bound that our alpha has to be larger than some value. But we don't want to do that, because that would again be assuming that our optimal parameter is larger than some bound. So what can we do? And this is the nice part. This is the where we get again to understanding the regularizers better. We can actually prove that the optimal parameter is greater than 0, here for the TV case, if a very natural condition or the data and ground truth holds. So this is here. So if the total variation of the noisy data is higher strictly than the total variation of the ground truth, then there is the optimal parameter is greater than 0. So this really means, because with 0 we would basically get back our noisy data if it's in BV. This means that there exists a parameter that improves the image. You get better image with respect to the L2 cost functional than your original noise image was. And also through this algorithm we're going to resolve the smooth problem. The solutions of the smooth problems also converge to the original problem. That was also another goal of this, but for understanding regularisers this is interesting. For TG we have a similar result now. We just have to show that for some second parameter of TGV similar condition holds, that the TGV of the noisy data is higher than the TGV of the ground truth. In that case, there exists a parameter alpha that will improve the image with respect to the L2 cost. We were also interested in another cost. The L2 cost is not very good actually. There's other better things invented, like the structural similarity measure, which better matches how we perceive images than the L2 cost or PSNR. The SIM is highly non-convex, so it's a little bit tricky to work with, but we came out with using just TV itself as a cost. But we couldn't really analytically do TV itself, so here we basically discretize TV on Huber regularized TV and use that as a cost. And then we get for the TV denoising case, in some sense, that the noisy data has to have higher total variation than going from the noisy data a little bit towards the ground truth in terms of the total variation flow. In that case, there again exists some parameter alpha such that we will improve the image by using that parameter or any parameter near it, really. And for total generalized variation, we get a similar result. I won't go into that. Here we again see the result says was the original image, noise image. We have computed TV solution for all alpha in some range, and we can see here at the near 0 at the cost starts increasing quite quickly. So the optimal solution really doesn't go to 0, which is indicated by these dots. Same with TGV, here it's alpha and beta on the different axes, and especially with respect to alpha we cannot really go to 0 because the cost increases quite fast. With respect to beta it doesn't really increase so fast. Same for another image. We really stay away from 0 parameters, so there are really parameters that will improve the image under very natural conditions. Okay, that just says that there are parameters for regularisers that will improve the image, but then how to decide which regulariser is the best one? So is TGV better than TV really, or maybe it's ICTV that's the best one, although people think that TGV is the best one. Well, for this I don't have analytical results. It would be interesting to have, but so far there has been no opportunity to do that. But we use the bilevel learning framework numerically on a large collection of images, this so-called Berkeley segmentation dataset, or which one is it? It has 300 images. I think there's only a few of them. And then we learned the optimal parameter over the whole collection using the two different costs. Well, this is the L2 cost for all TV, ICTV and TGV2. And also looked at the SIM, PSR and F, and there's some color coding going on here. So in each small image, the top row is SIM, the second row in there, because there's the kind of 3 boxes here, is PSNR, and the bottom row is the cost functional, which is kind of the one you should really look into, because that's the optimized one. And then whenever the box within the small image is red, then TV was the best for that image. Well, you don't see much red there, so TV is rarely the best one for the optimal parameter. If it's green, ICTV is the best one. There's quite a lot of green there. And if it's blue, then DGV2 was the best one. There's a lot of blue there, but actually there's a lot more green. So it would seem that ICTV is the best one. Again, the same thing, but now for the Huberized total variation cost functional. Now there is more blue than in the previous image, so DGV2 is performing better, but still it turns out that there is much more green. So if we do some statistic to like a 95% t-test on the results, it says that ICTV works best, which is quite contrary to what many people think. Now, you should take this a little bit with a grain of salt, because to perform these computations we used quite small images, and that smallness may make the images a little bit more chaotic. And visually, in detail inspecting the results, DGV2 seems to perform the best when you have large smooth areas, not flat areas, because then when you have cartoon-like images, that's where TV performs well. But if you have smooth, non-cartoon-like areas, DGV2 seems to visually perform best. But according to this statistical experiment, ICTV performs the best. But that's the end.
Thank you for this interesting talk. So we have plenty of time for questions or plenty of time for a break. Oh, just questions. Please.
When you use the inequality TVF bigger than TVF0 or something, you mean this is the minimizer itself?
You
the minimum energy is bigger than.
You mean
this one? This kind of thing.
No, this is
what
just.
Does this mean?
This one just means that if you have some data,
yes.
Let's say you have some noisy measurement f, then the total variation, the noise should have increased the total variation of the image compared to the ground truth that didn't have noise. So that's something very natural to expect for noise to do.
What do you mean by it's improved? How do you quantify?
So that's according to the cost functional. So I had this bilevel learning model here, which finds the optimal parameter. So the result says that there exists an optimal parameter which is non-zero. So the best cost, which in that first result was the L2 cost, like this. The lowest cost is achieved by some alpha which is non-zero. And that says basically that the cost is improved from taking the noisy data, because with alpha equals 0 you in principle get back the noisy data. Although there's some issues that the noisy data might not be in BV, but if the noisy data is actually in BV, then it really says that.
So numerically it doesn't matter anyway.
Well, this is analytical, so this is in space of functions of bounded variation, which will probably extend to discrete cases, but this is not done on discrete data.
For the bilevel case, you have to compute the solution also this parameter.
Sorry?
the
Yeah,
parameter.
there's for example in this, well, these are just for single images here. The red one is found numerically. That's the optimal parameter.
How did you compute this numerically?
The original one is what was already basically used by correlation and Juan Carlos Rodriguez in their earlier paper. Well, they use like Hintermüller-Stadler for the inner problem, but you can really use any algorithm you want for the inner problem, and then you need to be able to compute the adjoint equation for the inner problem to compute a gradient for the solution mapping. Once you have that, then you can use again any algorithm you want for the outer problem. We used BFGS, but again, you can really use any algorithm you want.
Sorry, just another technical question.
Yeah.
When you have the PV minimizer of this regularized problem, can you say anything about the level set of the minimizer? Are they sort of
So, you mean like here, the
how
level?
likely they are Jordan curves?
Sorry?
How likely they are Jordan curves? Or
Jordan curves, I don't know about that.
no,
But-
I mean
but-
regular, they are curves rather than a patch or something.
Like the level sets are, I don't know about their structure really, but we thought originally that maybe, especially the one-dimensional case would be quasi-convex. But I've heard that there's some recent research that shows that they are not even quasi-convex, these sets. So that also means that the level sets are not convex always.
Not, they are curves or not? This is the question.
Well, it depends on your definition of a curve. Like the boundary of the level set is some kind of curve, but whether it's a smooth curve or so, I don't know.
Are they one-dimensional or not?
But that depends again on the number of parameters.
If you fix the parameter, you just look at the level set. V
Oh, you mean
constant.
the solution set?
Yeah, that's the
The level sets for the inner problem, not the outer problem.
whatever.
Because for the outer problem here, for TV we only have one parameter, for TG we have two parameters, so that
No, just
that-
for TV. So if you set V equals a constant,
mm,
the pre-image is not a curve or not? It's a one-dimensional object or not in 2D?
I don't quite follow, but
Okay,
maybe we
doesn't
can.
matter.
Okay. If there are no further questions, let's thank the speaker again.